Have you ever actually stopped to think about how our incredibly delicate electronic devices, our phones, laptops, smart appliances, manage to survive the absolute chaos of raw electricity? I mean, seriously, just one unpredictable, violent spike in voltage could completely fry a microchip in a fraction of a second. Yet, somehow, they survive. So, how exactly do engineers protect them?
Well, welcome to this explainer. Today we're diving deep into what I like to call the electric sculptor's toolkit. We're going to get up close and personal with the foundational analog circuits that engineers use to literally shape, manipulate, and totally tame raw electrical waves into safe, useful forms. It's kind of like magic, but it's just really good engineering.
Here is our quick roadmap for today. First up, transforming waves with integrators. Then, we'll look at clipping circuits, basically signal scissors. After that, real-world clipper applications, and we'll wrap up with clamping circuits, which act like signal elevators.
Okay, let's jump right into Section 1, transforming waves with integrators.
So, the integrator. This isn't just a tool for making tiny little tweaks. No, it's used for completely transforming a raw electrical wave's shape into something entirely new. At its core, an integrating circuit is just a simple RC series circuit, that's resistor and capacitor, where the output voltage is directly proportional to the mathematical integral of the input. But to make this actually work in reality, engineers have to follow some pretty strict rules. The time constant, which is just the resistance times the capacitance, has to be massive compared to the time period of the input wave. Oh, and the value of the resistor? That needs to be at least 10 times larger than the capacitive reactance.
When you look at the basic setup, you've got your resistor and capacitor working together, and the effect? It is absolutely wild. If you feed a harsh, blocky square or rectangular wave into this setup, the output is sculpted into a perfectly smooth triangular wave. The circuit is literally summing up the input waves at any given instant, so it increases to a maximum and then just beautifully, smoothly decreases. It is a complete physical transformation of the signal right before your eyes.
Moving right along to Section 2, clipping circuits, our signal scissors.
Now that we've smoothed things out, let's look at a totally different tool, the clipper. You can think of this one like a really sharp pair of electrical scissors. Its whole job is to just snip off a portion of an alternating current signal. Depending on what we need to do, engineers basically rely on three main types of clippers. You've got the positive clipper, which cleanly just chops off the positive half cycles of the voltage. Then there's the bias clipper, which uses a battery to chop away a very specific portion of the wave above or below a set voltage limit. And finally, the combination clipper, which goes to town and snips away portions of both the positive and negative half cycles at the exact same time. To see this in action, check out a combination or symmetrical clipper. By setting up two diodes, it builds these firm barriers, limiting both the positive and negative peaks to a specific barrier voltage, let's say something like 0.6 volts. So if you feed it a smooth rolling sine wave, it aggressively chops off the top and bottom peaks, effectively turning that smooth wave into a reasonably square wave output. Snip, snip, done.
So why do we care? That brings us to Section 3, real-world clipper applications.
I mean, it's cool to look at these shapes changing on a graph, right? But how does this actually help us in the real world of modern electronics? Well, in practice, these diode clippers act as absolute lifesavers. They're the ultimate gatekeepers. Imagine a dangerous rogue voltage spike racing down the input line, heading straight for a delicate digital circuit. Instantly, a diode clipper becomes forward biased and conducts. It acts like a bouncer, intercepting that violent spike and safely shorting it directly to the ground. The VIP digital circuit, totally safe.
And what exactly are these bouncers protecting us from? One word: transients. A transient is a sudden, extreme rise in current or voltage that lasts for just the tiniest fraction of a second, but man, they cause considerable damage. If those clipper diodes weren't standing guard, these transients would blast right into the heart of our electronics and completely destroy our digital technology. Literally game over for your devices. But thanks to clippers, the danger is snipped right out of the wire.
Which brings us to our final tool. Section 4. Clamping circuits, the signal elevators.
All right, so we've smoothed waves and we've chopped them up. But let's draw a really hard line between those tools and this final one. While clippers cut and completely change the physical shape of a wave, clampers do something entirely different. Clampers act like elevators. They add a DC component to the signal. This means they preserve the exact shape and the original peak-to-peak value of the wave perfectly, but they shift the entire waveform vertically, straight up or straight down.
Now, to pull off this elevator trick, a clamper relies heavily on our old friend, the capacitor. And it follows two super simple, absolutely fundamental rules. Step 1, the charging time of the capacitor has to be extremely small. We're talking tiny, like 50 microseconds, so it can charge to the peak voltage almost instantly when the diode conducts. Step 2, the discharging time has to be massive in comparison, say 50 milliseconds. This ensures that during the off time of the diode, the capacitor stays almost fully charged, holding that voltage totally steady to push the signal up or down. Okay, want to hear a really cool engineering cheat code? There's a super straightforward visual shortcut to figuring out these schematics. Just look at the diode. If the diode is pointing up, away from the ground, boom, you've got a positive clamper. If the diode is pointing down towards the ground, it's a negative clamper. It is literally that easy.
So, in a positive clamper setup where the diode is pointing up, you can see how an input square wave that normally dips between positive and negative is pushed entirely upward. And that's all thanks to the capacitor holding that charge we just talked about. The shape hasn't changed one bit, but the new negative peaks now perfectly rest on the zero level. This fundamentally changes the peak value and introduces a brand new average DC value to the waveform without ever distorting its original shape. Pretty clever, right?
As we wrap up this explainer today, I want to leave you with a quick thought. We live in a world that is totally obsessed with the latest digital microchips and massive, complex processors. But honestly, none of that incredible digital logic could even exist or survive for more than a few minutes without these heavy-duty analog sculpting tools. The integrators, the clippers, the clampers, they are all working tirelessly behind the scenes to shape, elevate, and protect every single electrical signal. It really makes you appreciate the unsung analog heroes of electronic design, doesn't it? Thanks for learning with me today.